In Unit 3, we'll look at pseudopolynomial algorithms, the first example of something where we can take an NP-hard problem and still do something about it, at least for some problems. And this will be a relatively short unit. There's not a lot of deep theory in there, but it's a cute observation and is a good segue into the next unit. So we'll start with a little bit of a definition just to set the stage. This is a lightweight and slightly vague definition. An integer input problem. It's just some problem. Can be an optimization problem or it can be a decision problem, where part of the input, the instance, consists of numbers. So formally you could say it's some arbitrary string and then a sequence of integers. All that we really need here is that for a given input, I can say what's the largest integer that occurs as part of this instance. So again, we've seen some examples before, and if we pick TSP as the prime example, max int would just be the largest distance that occurs in your distance matrix. So simple definition. The point of this is just not all problems are integer input problems. Sometimes the input is all about strings. Say this closest string problem where I'm giving a list of strings and okay, there's how many differences do you allow? But if you say the optimization problem of that, then the input would just be strings, then there's no integer associated with that. Now, as a warm-up, let's think about how big or small this max int can really be. Because that will determine how hard we have to work in the following. Okay, I'll switch over. Yeah, just about fit all on the slide. I guess 11 people is mostly it, so here's your votes. And you can select more than one answer. And because these are big O bounds, many of them are true. Let's discuss this briefly. So all of these are possible as how big max int can be as a function. So the extreme case clearly is that my input is just a single big integer. Okay. Then it could be still a tiny number if I somehow prepend it with lots of zeros, or maybe it's not the only thing in the input. It could be really small. What's the largest it can possibly get? I can use all the space I have for digits of a number. I could certainly write down 2 to the n. 1 with n zeros, something like that. Now I can do slightly bigger because in general my input alphabet isn't restricted to binary, and so I can effectively achieve, so this constant in the exponent is just transforming the basis to a different constant. This is essentially c to the n for any c, for any constant c. And by using a larger alphabet, I can achieve that. It's a bit cheating in the sense that we think of n as being the same, independent what the alphabet is, but the Turing machines always force the alphabet to be constant size. So in a way, it's okay. But you can debate about this, and maybe it's enough to do binary numbers, especially because I put binary here on the slide. So it's maybe a bit unfair. But clearly there's an upper bound. You cannot go above that. So also this max int cannot be arbitrarily bad. Okay, it can, for example, not be doubly exponential, and is certainly always bounded in terms of the input size. By the way, if you're wondering how to specify an integer without telling you up front how many digits it uses, there's a nice solution that some of you have seen in efficient algorithms. Suffice it to say, it's possible, even if you just have binary alphabets. Of course, with more alphabets, it's easier. You just put a special symbol as end of number. Okay, so still, it could be exponential. That's the point, which means if some algorithm has a running time that depends on max int, it might be an exponential time algorithm. Nevertheless, we'll do the following definition. We call an algorithm pseudopolynomial if its running time is a polynomial of the size of the input, n, and this max integer. So in particular, this means that the overall thing could be exponential. So pseudo-polynomial time does not mean polynomial time, right? That's quite clear. That's why it's only pseudo-polynomial. Now, maybe this term is not great. And there's another term, quasi-polynomial, which means something entirely different. I just put it there so you're not confused. It will not pop up in this lecture, but in this module. If you just vaguely remember, it was something like polynomial. The term is not super great. It's not quite polynomial. But why do we call it pseudo-polynomial? At least it has some form of polynomiality if this max int is small. Right? That's where the name comes from, I suppose. Specifically, if we can bound max int by some polynomial in the input size, then the overall thing is also a polynomial, a different polynomial. That's just because if you insert, say, max int of x is, and we use n as the length, right? Maybe this is less than n to the 10th, right? And then maybe this p is, I guess, two variables, n and m, is less than n times m to the 5th. Then if you insert this for m, n times n to the 10th to the 5th is a lot, but it's not infinite. It's n to the 55. N to the power 55 is not a running time that we would like for any practical algorithm, but it's polynomial. What I'm saying here is, if you insert one polynomial into another polynomial as one of its variables, it remains a polynomial, just of different degree. So if maxint is bounded by a polynomial, a pseudopolynomial time algorithm is actually polynomial time. Okay. To grab this formula, this another definition. We take a problem u, and we take a bound on the maximal integers that are allowed. And then we say value of this bound, subscript u, is a new problem, but one where I'm only allowed to use inputs where the max int is small, smaller than h. Okay? So think of all the TSP instances where the distances are at most 10, or a function of the input size, at most square root n. That's up to you. And then we can have this this little theorem. We have an integer input problem, and we have a pseudo-polynomial algorithm for this problem. Assume that exists. Then indeed, for every polynomial h, if we restrict this problem to only max int smaller than h, there's a polynomial time algorithm for this subproblem. So this A has a running time which is given by some polynomial O of P of the input size and max int, a lot of parentheses. So if we're given some input in this restricted value problem, value h of u, then for this instance, max int is at most h of x. Right? And this is a polynomial, so this is order n to the c for some constant c, depending on this polynomial h. And so the running time of the overall algorithm is we just insert n. I'm using n again for the size of the input, as always. And max int is this, so order n to the c. And that's another polynomial, just as we discussed now, for another constant d. And so A runs in polynomial time for all x in value h of u. Okay, that's all there is to prove here. And so if this is a decision problem, then the value restricted problem is in P. If it's an optimization problem, the value restricted problem is in PO. Works both ways. It doesn't matter what the algorithm does, if it decides and just outputs yes, no, or if it actually finds a solution.